everyone, we are back and we are going to talk now today about a very important topic, which is beam bending. Now, obviously there are lots of different types of applications where beam bending is important. So you could think of a bridge and a car driving across a bridge. You can think of basically like a swimming pool and you're jumping, a person is jumping off of, a diving board. But there are also some very, very important applications where, and some exotic ones too. So you can think of, there's a technique called atomic force microscopy, where we have basically a tip here that's functionalized with a little ligand, and on the bottom is another ligand where it binds to, A binds to B, and depending on the deflection of this beam, we could actually measure the force between these interactions. There's also lots of different applications in buckling that are associated with cellular and biomaterials too. So lots of different applications and exotic applications where beam bending can occur. But before we get started today, we want to do some review about some of our beam bending basics. So, and specifically how we want to define some systems. So let's go ahead and do that today. So whenever we're doing a beam bending problem, again, we need our coordinate system. So X and Y, 1, 2, 3. So always define our coordinate system. And additionally, when we have different types of support, so I typically call this a fixed support. So it's a cantilever beam, but let's say at X equals 0, and if this is some length beam L, we're going to have different boundary conditions here in terms of how our beam is going to respond. So we should know that at this fixed support, we are going to have basically a corresponding basically force in the X direction, a force in the Y direction, and a corresponding moment as well. So there's some moment that occurs. We don't know what direction it is necessarily. So additionally, we have these reaction forces, we have this reaction moment if there's a force applied to the system. We also know that if I look at this system here, and if I'm looking at a deflection of the beam in terms of y, at this position, x equals 0, my displacement, let's just call the displacement v, for example. Displacement v at x equals 0 is going to be 0. Additionally, we'll have that the slope at 0 will also be 0. And we'll get into more of this later on when we get into some beam bending basics. But we want to know that we're going to have reaction forces and reaction moments here. If I just have a pin, for example, if I have a pin here and a pin here, I'm going to have a reaction force in the X and in the Y at both of these locations of the pins, but I'm not going to have a reaction moment. So I could effectively say again that the moment at this 0 location, and if this is of length L, the moment here and the moment here is equal to 0. Moment at L. So those are important boundary conditions that we can identify here. And the same thing you can see for rollers as well, though we're not going to use rollers. Also for frictionless surfaces as well. So additionally, we also want to, and we're going to be developing basically shear bending, or basically shear force and bending moment diagrams. So we want to determine sign directions, sign notations, and basically what are we going to define as positive and negative. So again, counterclockwise rotations, positive, clockwise rotations, negative. If we have a beam that creates a smiley face, that is positive curvature. If it is negative, sad face or sad mouth, that's going to be negative curvature. Curvature is kappa, which is 1 over our principal radii. So if you were to draw a circle with the radius of curvature. So again, that's important as well. And we can see kind of what values there are as well. Additionally, if I make a cut in a material, a positive shear force will be going in this direction on the side that's closest to the cut, and then on the opposite side it'll go up, and then vice versa, obviously, if it's a negative shear force. Although again, we're going to be taking a different fairly cool technique to kind of avoid some of those ambiguities in making cuts in beams. And again, the key point through all of this is that we need to remember we have our equilibrium conditions, so the sum of the forces on the moments must be equal to 0. And we can identify that, just kind of as a quick reminder to ourselves. We can do a quick problem with the cantilever beam. So if I apply a load here, the sum of my force in the y must be equal to 0. So I have a reaction force here. I also have a reaction force in the x, but since there is no other force in the x and the sum of the force in the x must also be equal to 0, then even though this is positive fx must be equal to 0. So I can solve for my force in the y, it must be equal to p, and then the same thing for our moments. If I calculate it, the moment, for example, around this point here, this origin, if I calculate the moments around here, there's going to be some m naught, some m going here. That's our reaction moment. That's positive. Negative because, again, I'm going clockwise, so clockwise in this direction. So that's going to be minus p times, again, my perpendicular distance, which is going to be our length. So again, we have to do our right-hand rule. So line of action. So perpendicular distance to the line of action, that's going to be L. Right-hand rule, and we see it's negative. And that would be how we found these moments. So hopefully that jogs some memories. And next time we are going to get into, and actually a lot of these are hopefully some review from statics, but we are going to get to how are we going to determine and actually express stresses in beams. So that is going to be our key, our work moving forward. And hopefully you can review those extra notes at your leisure. So we'll see you then. Thanks. Bye.